Okay, so everyone, welcome to today's paper club. You can join.
I will.
Okay, cool. So welcome to today's paper club. What we're presenting today is actually not properly a paper. It was a new architecture, a merge of two architectures that was presented in a workshop. On deep learning recommender systems. The abstract itself is very short and not very informative, I think. But since we found this to be a quite interesting premise, we decided to test it ourselves. So I'll also be demoing our test with this architecture. The code that I'll be using today, I put it on my GitHub repo. So you can look for CA Ledesma white deep model. I'll put the link in the meetup as well. If you want to download the code, please do it. If you want to contribute or you think that something might improve the models, please also put it there. Create a pull request, and I'll be more than happy to look into it. Hopefully with the experiments and whatnot, we'll be able to generate a bit more of a discussion. So if at any point you say maybe this layer would be better or this other model would be better, please just give it a shout and we'll talk about it. Sounds fair? Cool. So about the paper, the abstract itself, of course it's very short because it was in a workshop, it's not a proper paper. But it is framed within recommender systems. So the typical challenge within recommender systems is that you need two things. The first thing is that you need memorization. So you want, let's say you want a system, well, let's just use the example. You want a system that if you have the Netflix app, it's going to recommend you another app that is similar to Netflix. You need the machine learning system to memorize these sort of relationships. So if in the past you have liked Netflix and I think it's Pandora, the one they say here. If you like Netflix and Pandora, you want that in the future it will recommend you the same things. But that's a memorization system, okay? So that does not generalize very well. It is not capable of producing sort of exploratory insights on recommendations, right? These memorization models, they are very useful. They are normally very sparse inputs. So if you have a recommender system like the one they explain here, it would be one input layer containing all the apps, for example, and then you have a one in the apps that the person likes or that the person has downloaded. And then you make some sort of cross product and it's still a very sparse vector. And you put that through a logistic regression and it gives you a system that memorizes everything that is in the training set. So the problem with that is that it doesn't generalize. As soon as you put in new examples, it's going to fail to recommend proper things. So the sort of state-of-the-art systems that generalize well are deep models. Go for it. Thank you. So the state-of-the-art systems that generalize well are deep models, and in contrast, to wide models, deep models have dense inputs, so they are not sparse. And they will have a number of hidden layers. They'll have a number of hidden layers which will calculate further representations of the input features in further dense vectors. And then you will have an output unit which is going to try to make the prediction. Again, the strengths of this kind of models is that they are capable of generalizing very well. And they're able to provide new recommendations for inputs that were not seen in training. But the downside is that sometimes you want that memorization capability. So sometimes you want the system to memorize certain things and to generalize on other things. So what this abstract proposes is actually a mix of the two systems. And what they claim is that this system is capable of both memorizing known relationships and generalizing as well to new examples. So the abstract itself, it goes a bit further than just proposing this wide and deep architecture. Another interesting thing of this is that it is easily deployable. So it is fast to compute in almost real time. And it is also fast to retrain in almost real time. So This was of course developed for the Google Play Store recommendations engine. So if you imagine how much traffic they get, it is quite massive, and you want the model to continue training as it receives new training samples. So they also explain the transfer learning system and why it's important for it to generalize. So the overview of the system is actually something that you might be familiar with, because both the models are very simple. The white component is simply a linear, they use here a logistic regression, but it's simply a linear regression mechanism. So you have all your input features X, and you want to predict your output class Y, and you do an affine transformation of the inputs, and you get your outputs with a bunch of trainable weights. And of course, the feature set includes the raw input features and also some transformed features. Namely, they propose this, well, they don't propose, they use this cross-product transformation, which is helpful for memorizing these different relationships. So here you will get a 1 if both the things that you're looking for exist in the user. Okay, so you get a sparse vector which also contains information about the user. So in this case, speaks English, is female, and then you can also cross product it with the apps that they have downloaded, the country, a bunch of other features that they have here. So you have a bunch of features, and you get this huge vector, which is unique for each user and has ones in the places where you have co-occurrences of certain features. Okay, it being age, number of app installs. They have 3 dots here, which means there's a lot more information here. So that's the white component. It's actually very simple. And the deep component is, as you would expect, the white component is the cross-product transformation. Okay, so you have this huge sparse vector of co-occurrences for the white part. And for the deep part, you do a little bit more of feature engineering for as you would in machine learning. And what you got is a traditional feed-forward multi-layer perceptron. And you have all your continuous features. They are normalized using a strategy with a quantile so that they are all between 0 and 1, so as to keep the numbers bounded. And you have, for the categorical features, you have embedding layers. And does everyone know what an embedding layer does? No? Yes? No? No? Okay. Okay, very quickly. When you have a categorical feature, of course you cannot put it straight into the machine learning model. So what you have is the easy way to encode a categorical feature is with a one-hot vector. Okay, so let's say you have, I was going to say Chandra, but maybe not. Let's say you have a categorical feature x, and that x has 4 possible values, x1, x2, x3, and x4. So there are 4 in x1. So there are 4 possible values for this categorical feature. The easy way to encode it is to say that for a given example, xi,